So today we're going to talk about the logistic regression and its application in classification and as well as prediction. So I'm assuming that sign-in is going to be done sometime throughout the lecture. And so the learning objectives are already when you do the survey, you will see a list of learning objectives. So they're mostly in line with what I'm planned to lecture, but sometimes I may move a few things between lectures. Today we're covering logistic regression, multinomial logistic regression, and some evaluation of prediction accuracy. So last time we talked about associating a univariate variable on the left-hand side of a regression equation. So a response variable that's continuous, we try to associate it with multiple predictors through regular linear regression. And today we're going to consider a different type of response variable. Instead of being continuous, we'll focus on categorical response variable. Before we move to that, I would like to think about if it makes sense to run a linear regression for example, for a binary outcome variable. So in this first plot, we have x as the IgG level, and Y is the status of HIV infection at week 28 of the study. So we want to see if the IgG level is going to protect some of the subjects from getting HIV at 28 week. And if you plot the data using scatter plot like this, with no HIV as 0 and yes to HIV as 1, you will see something like this. And if you just treat the 0 and 1, yes and no, as the response variable in the linear regression, you would fit a straight line to describe this data set, which doesn't really make sense. And this is another case where the predictor, instead of being antibody level, is now the three races. This situation variable as dummy variables 0 and 1, you will end up with a bunch of dots at 0, 0, a bunch of dots at 0, 1, 1, some dots at 0, 1, some dots at 1, 0. And if you just fit linear regression with those data set, you're using a line to describe 4 clusters of dots, which also doesn't make much sense. So the framework of linear regression doesn't really allow you to fit models where your response variable is binary or categorical. So we need some different distribution. To start with, for simplicity, we're first going to look at a response variable that is binary. And a binary variable can be described the distribution of a binary variable can be described using something called the binomial distribution. Many of you have probably already learned it in undergrad stat classes, but I'm going to do a brief review of what a binomial distribution is. So a random variable follows a binomial distribution n and p. So here are the two parameters of the distributions, but the first parameter n is a given number, so we don't typically consider it as a parameter. So n is a given number that we know, and p is an unknown parameter. And the distribution of the binomial distribution can be described by this probability distribution function. For example, if your variable takes value 0, then the probability of the variable taking 0 is you plug in y equal to 0, you will end up with 1 minus p to the power of n. This should be capital N, sorry, there's a typo. And if you have, if you want to get the probability of observing a 1, you plug in the 1 here. And if you want to know the probability of all y equal to n, you plug in y equal to n there. So the probability function describes the probability of this random variable taking each value in the range. If you only have n equal to 1, then your random variable will take value only at 0 and 1. This is also called a Bernoulli distribution. This is the one random distribution that describes a binary variable. There's only one parameter p here describing the probability of having 1 instead of 0. For example, if you consider the probability of one little infant getting respiratory infection in their first months of life, that probability, if we denote it as P, then whether the infant gets the infection or not in the first month, that is a Bernoulli distribution. Getting infected is yes, is 1. Not infected is 0, no. And this one distribution just have you just use this binary distribution to describe whether this infant get infected or not in the first month of life. What you observe is 0 and 1, but the underlying parameter is a probability between 0 and 1. It's a continuous number. And if you have 100 infants, then the number of infants among these 100 that got infected in their first month of life, that number will be a random variable. It can be 1, it can be 2, it can be 100, depending on how infectious how much respiratory infection is going around. But the expected number of infants among these 100, that is the population mean, and it will be 100 multiplied by the probability. So the binomial distribution is, as you can see in this example, this is when you have 100 infants, this is a binomial distribution of 100 and p, where 100 denote the total number of yeses you can have, you can possibly have, and p denote the probability of having yeses. You also see this this distribution describe the distribution of getting heads when you flip a coin, or the probability of winning lotteries. So this is a very useful distribution, and we'll use the Bernoulli distribution to describe binary variables and try to use it to connect your binary variable with a bunch of predictors. Here I'm giving you a few examples of binomial distribution. The first one has a total number of 5, and the probability of being 0.6. So you can see that the number of this is among, I'm taking 100 jaws. So this is the summary of 100 binomial random variable with total possible count as 5 and the probability of yes being 0.6. And among these 100, only a few of the random variables has a realization of 0. Most of them has a realization around 2 and 3, and a few of them around 5, because the probability of getting a yes, getting a 1 is 0.6, so it's slightly in the middle to the right. And that's why you observe most of the realization of this distribution around the middle to the right. If you set the probability to a very small number, it will be unlikely for you to observe a 5 in this distribution, and most of them will be 0. On the other hand, if you have a probability equal to 0.9, then you will likely not observe 0 and 1s and observe a lot of 5s. And if you just have a total number n here, this is Bernoulli distribution. When I draw 100 Bernoulli distribution from the probability parameter 0.6, you will roughly observe 60% of those random variables being being observed as 1, and 40% are being observed as 0. And again, if your probability of yes is 0.1, then among 100 runs, you will have about 10% of them being 1 and 90% of them being 0. So this probability is describing in this population how likely you're going to observe 1 instead of 0. And this is the parameter we're going to use to connect the observed yes and no's to the predictors. So the model setting is like this. We have binary, we now have a binary outcome variable, and we want to connect it with a bunch of predictors. Before, when we have continuous random response variable, we can just use a linear combination of the predictors to describe the population mean of Y. So the population mean of response when it's continuous, it's just a linear combination of predictors. But when Y is binary variable, the population mean is between 0 and 1. You cannot model something between 0 and 1 by a linear combination of predictors, because this linear combination is going to range from negative infinity to infinity. So there's a mismatch in the range of values you can take between the population mean of Y and the linear combination of predictors. And how do we solve this mismatch? The key is through this thing called the link function. So we just need something to transform a value between negative infinity to infinity into something between 0 and 1. And what we can do is to use a logit function or xspit function as its inverse function. So here on the left is the xspit function. The xspit function takes input of a real value between negative infinity to infinity and transform it into something between 0 and 1. The logit function is the reverse of it. It transforms a probability into real value. So these functions will help us connect the linear combination of predictors and the probability of yes and no for your binary response variable. The xspit function is going to be used on top of the linear combinations. So here, this f function will be your xspit, will use xspit function in place of this f. And after the transformation of xspit function, the linear combination of predictors in a real range will become a probability. And this probability will be used to describe the response variable that is binary. And the reverse of that transformation is making the probability back to the predictors, linear predictors. This function is called the logit function, and that's where the logistic regression's name comes from. So right now, our model setting is like this. We assume that the linear combination of predictors affect the outcome through this transformation. The linear combination of predictors after xspit transformation is the population mean of your response variable Y. We are not directly associating the predictors with Y, because Y is 0 and 1. It is a random variable that is it is the observation of the random variable. We are not directly modeling 1 and 0 with this with this linear combination of predictors. We are modeling the probability of observing 0 and 1s. That's major that's a very important very important point we need to remember when we model linear regression. We're not setting y directly related to x. We're setting y related. We're setting the population mean of y related to the predictors. And in this case, the population mean of y is the probability parameter. So this is the deterministic relationship we're modeling, not between y and x. Do we have any questions? So if we do not have any questions, I will move on to the interpretation of the parameters. So in linear regression, the interpretation is pretty straightforward. You look at the x, you will see the change of x directly reflected in the expectation of y through the parameter, through the regression parameter. But here, the change of when you change x by 1 unit, it's reflected on the p in a nonlinear way. So before we get into the specific interpretation, we need to introduce this concept of odds. So what is an odds? The odds of one event happening is the probability of that event happening over the probability of that event not happening. This concept is used a lot in gambling. So if you have, for example, Eagles versus the the Kansas Chiefs. So the probability of the Eagles win divided by the probability of the Chiefs win. That is the odds of the Eagles win. So when you look at odds, you pitch two things against each other, the probability of one event happening over the probability of the other event happening. And there are only two events happening in total. So that's the odds. And the odds equal to 1 is exactly equivalent as the two events having equal probability of happening. So probability of one event is half. If your odds is larger than 1, then the event on the numerator has a larger probability of happening. If your odds is smaller than 1, then the event in the denominator has a larger probability of happening. And going back to the model setting of logistic regression, the probability of our response variable being 1 is modeled as this XPIT transformation of linear combination of predictors. And then if you look at the other way, the probability of your response being 0, that's 1 minus the mean, the probability parameter. And it turns out to be this function. So the odds of observing y equal to 1 is going to be the probability of 1 over the probability of 0. And it turns out to be the exponential transformation of the linear equation. And if you want to interpret one specific parameter in this linear equation, you can then look at the odds of the original value and the odds of this equation when you have, for example, x1 increased by 1 unit. In this equation here, I'm pitching two events against each other. The first in the numerator is the odds of y happening, y equal to 1, when x is increased by 1 unit. In the denominator, it is the original value of x. So I'm taking a ratio of two odds. That's why we call it the odds ratio. So this is describing the ratio of odds when you increase x by 1 unit compared to the original. And this odds ratio is exactly the exponential of beta, the beta being the regression coefficient of the x you increase one unit on. So here I'm increasing the jth variable by 1 unit, and the odds ratio is quantified by exponential of beta j. So beta j is also called the odds ratio of xj. When you have a continuous xj, then this odds ratio means that this beta j can be interpreted in this way. When you increase xj, for example, age, when you increase age by 1 unit, then the odds of y equal to 1 is multiplied by this value. And this is assuming all the other predictors stay unchanged. If you have a categorical xj, then the interpretation is similar. Instead of increasing 1 unit in xj, you're changing 0 from 1. So for example, if you have Black as the baseline group, and you're looking at the regression coefficient of Hispanics, then that regression coefficient can be interpreted as the odds of Hispanic having y equal to 1 over the odds of Black having y equal to 1. That value is this exponential of beta j. So this is the ratio of Hispanic over Black in terms of their odds of y equal to 1. So suppose that in a lung cancer study, where y equal to 1 denotes lung cancer and 0 denotes no lung cancer, and x equal to 1 denotes smoker, x 0 equal to 0 denotes non-smoker, and the smoker status, this smoker variable has a regression coefficient of 5. How do we interpret this coefficient of 5? So remember, odds is, so if you look at beta equal to 0, beta equal to 0 means that the ratio, the exponential of 0 is 1. So these odds are the same. So the odds ratio is 1. Beta equal to 0 means odds ratio is 1, which means the probability of these numerators and denominators, they're the same. So that means that changing x is not changing the probability of y. So in other words, your x variable has no effect on the odds of y when the other predictors are accounted for. That's how you interpret a zero regression coefficient in the logistic regression. It means no effect on the odds or probabilities of y happening when the other predictors are accounted for. If your coefficient is larger than 0, that means that this ratio here, the odds ratio, the numerator is larger than the denominator. It means that the numerator even has more probability happening, more likelihood, is more likely to happen. So you can interpret as xj has a positive impact on the probability or odds of y happening when the other predictors are accounted for. So when we have a beta equal to 5, it means that smoking is going to multiply the odds of having lung cancer by exponential to the 5. That is a big number. So that is the multiplication you put onto the odds when you compare the two groups. If beta is negative, then your numerator has a smaller probability of happening compared to the denominator. So you would say xj has a negative impact on the odds or the probability of y. So for example, exercising, can have a negative coefficient. And in that situation, you would say exercise is protective against lung cancer. And suppose that coefficient is -2, then you would say the probability, the odds of having lung cancer is going to be cut by half if you exercise regularly. In our example, we have the probability of, we have the event having HIV or not at week 28 as the response variable. This is yes or no binary variable. And we're using, this is a composite risk factor that we estimated from the behavior of the subjects. This is age and this is their ethnicity. Of course, you can put in other predictors to predict the HIV status at 28, but these are the variables we use as examples. So the composite risk apparently has a very significant impact according to the outcome because the p-value here is quite small. The other variables do not have a small p-value. If we use the alpha of the type 1 error of 0.05, we will say that the composite risk score has impact on the HIV status while accounting for the other predictors, and the other predictors do not have a significant impact. And to interpret these coefficients, for example, for the risk score, this is a positive coefficient. So it's actually saying if you have a higher risk score, you're more likely to be infected by HIV at 28 week. And how much risk how much increases in the risk, you will look at the exponential of this coefficient. We do not look at it alone. If you look at it alone, it's called log odds ratio. If you do an exponential transformation of it, it's called the odds ratio. And odds ratio is more intuitive than log odds ratio because it's the multiplication factor you apply to the odds. So here, if you take exponential transformation of this regression coefficient, it's 4.38. So this is the multiplier you apply to the odds if that person's behavioral risk score is increased by 1 unit. If you have 2 patients, that's exactly the same in race and age, and one has 1 unit higher risk score compared to the other, then the one with higher risk score, that person's odds of getting HIV is more than 4 times higher than the person whose behavioral score is lower. And if you want to interpret the age parameter, although this is not significant at the level of 0.05, if you're being very, very conservative and looking at the alpha of 0.2, then this is significant. And you can still interpret it, even if it's not significant. You can say, we observe an effect of this size, but it's not statistically significant at the level of 0.05. But the effect size, you can still describe it. And in this situation, if you take the exponential of the coefficient, when this is for Hispanic, then it's a smaller than 1 number. So it's saying that the odds is going to be reduced if you look at Hispanic compared to the baseline group Black. So the subjects, if you have 2 subjects, one Hispanic, one Black, and they have the same behavior score, risk score, the same age, then the odds of the Hispanic subject getting HIV is 71% of the odds for that Black subject. And you can also construct confidence intervals for these effects. And the 2 ends of the confidence interval also need to be exponential to be interpreted. So the lower end and the upper end of this regression coefficient is going to be real valued. You need to take exponential transformation of those two values to get the range confidence interval for the odds ratios. Any questions? Let's see the chat box. Oh, we do have some. Oh, it's Richard. Okay. So then after we learned about the interpretation of regression coefficients in the logistic regression, we'll move on to the inference. So there are two types of inference for logistic regression. One is the Walsh test, one is the likelihood ratio test. When you have a large sample size, these two are not going to be very different from each other. When you have a smaller sample size, then they might be slightly different from each other. I personally do not have any preference for one against each other. Richard, do you have any?
Yeah, I believe there's some literature out there that the likelihood ratio may be slightly more powerful for smaller samples, but as Pishi said, like at larger n, like your larger your sample size, they kind of converge and they're about equally powerful.
Yeah, thanks, Richard. The Walsh test is more intuitive because you can basically obtain that by looking at the regression output. It's a very quick hands-on calculation you can do. If you look at the ratio of this estimated coefficient over the standard error, you compared it with 1.96, you just get a z-test for that regression coefficient. So it's very intuitive and easy to calculate. And the hypothesis testing for these can be done in two sides or one side. And depending on which side you're comparing, you compare to you take you will look at the z-score itself or the negative of z-score. For example, if you are doing a two-sided test, then you just compare the absolute value of this z-score with 1.96 if your alpha is 0.05. If you have one-sided test and if your z is in the positive direction, then you're not going to reject it because your alternative is saying the other way. So you don't even have to look at the test. You, you don't have negative ones because they are telling you the other direction. But if your test statistic is telling the same direction as your alternative hypothesis, then you will need to compare with a normal quantile. And if your alpha is 5%, then the normal quantile is actually going to be 1.65. So that's the difference between your two-sided test and one-sided test. Two-sided and one-sided. And again, p-values have a correspondence between the two-sided test and one-sided test. Oh, is there any explanation to why HIV infection will increase among well, that is a very good question. I think that's something that is specific to this study population. So we did not collect enough variables to explain why, but for this specific population, subpopulation that we sampled from, the Hispanic has slightly lower risk.
And yeah, I'll just follow that up, that it's not statistically significant in any way, though.
Yeah.
Yeah.
So it can be just due to, well, it can be due to a few of the subject being outliers or dragging the effect to that side, but it's not significant. Does that answer your question? So thanks for the engagement. So the z-test is a very simple, straightforward way to test your regression coefficients. Most of the times we test it against 0. We say we want to see if that coefficient is significant or not. But there are also situations where you might want to compare with a non-zero value. For example, if you have a drug and you want to see if it's effective or not, and you're comparing it to an existing drug, then you probably want to put the effect of the existing drug as the null hypothesis and compare your new drug with that old drug by looking at that comparison instead of comparing to placebo or nothing, no effect. The likelihood ratio test is more accurate, more powerful test for a sample size that is slightly lower. So the test is not straightforwardly observed from the output. You will need to use another function to obtain it. So here I'm showing the example of testing for the behavior score being significant or not. Here I'm running a logistic regression model with age and race only. And before this model 1, here we run it with all 3 variables, behavioral risk, age, and race. So I'm doing one model with all 3, the other model without behavioral risk, and I will use the ANOVA function to compare the 2 models. And that comparison will tell us if risks or behavioral risk is significant or not. If the 2 models are not very different, then you would say behavioral risk is not a significant predictor. For this specific data set, comparing the model with and without and with risk score, we have a significant p-value. And this is very close to what we have here because this is a quite large sample data set. So your conclusion wouldn't change whether you use likelihood ratio test or the z-test. If you want to test for race, then you are basically removing 2 dummy variables altogether. So this is running age and behavioral score, and you compare it with the model running race as well. For this comparison, you can see the degree of freedom is 2 because when you remove race, you remove 2 dummy variables. Race has 3 categories, 2 dummy variables. So you remove 2 predictors altogether and comparing the model without race or without race versus with race. This p-value is not significant. So for this specific data set, race is not a significant predictor. Race doesn't have a significant impact on the status of HIV infection status. So the Walden likelihood ratio test for the linear regression is going to be the same, but for the logistic regression, they're going to be different because of the distribution change. For normal distribution, there's a nice matching between the Walden test, the z-test, and the likelihood ratio test. But for logistic regression, that that equivalence is broken. So you will have slightly different results. But most of the times, for large samples, you will have very similar results. So I would just recommend using the likelihood ratio test in general. The z-test is just intuitive. It's something that gives you it's the first message delivered by the regression output. And you can also obtain confidence intervals for the Wald test and likelihood ratio test. They both have confidence intervals. If you run confident function without anything else, it will give you the confidence interval based on likelihood ratio test. And if you run a confident.default, it will give you the two-sided interval for the based on the z-test. And after we get the regression coefficients and the confidence intervals, the natural question is, how are we going to use this model to predict future data? So if you have a new subject with age, behavioral score, and race, ethnicity, how likely is this person going to have HIV based on the the evidence from this data set? I'm seeing a question in the chat box. Is race not a complex determinant?
I,
Uh,
I think just that the fact it's, self-reported race within this population, and it's kind of it's a very tricky
yeah,
variable. I think for this example, we're using it as kind of an example in terms of just, something with 3 levels.
yeah,
But yeah, the actual biology or anything like that isn't really necessarily not that there even is a biology, I guess, behind it, as opposed to something like genetic ancestry. So I think in this case, it's being used as a for like learning purposes. But yeah, to understand like the complex potential social determinants of health that maybe are really possibly driving, if there was an association, which we're not seeing here in this example, um, would be a lot more complicated and more appropriate. I don't know if that answers your question, Franklin.
Yes, yes.
Yeah. Thanks for pointing that out. I appreciate it.
Thank you.
So if we consider a new subject with the values of the predictors known, but the outcome still unknown, we can then evaluate how likely this person is going to get HIV at 28 week. And if that is high, then we probably want to adjust our intervention procedure based on what we predict. So that's the usefulness of prediction modeling in the logistic regression. If we want to use this specific data set as an example, we just need to plug in the estimated coefficients into the regression equation, and then plug in the observed value of your new subject, and then calculate the probability of having 1 or 0 based on what we have, the evidence from existing data and the observation from the new data. So that prediction is going to be a probability. And you can also transform it into odds or log odds. So log odds is actually what the linear combination of the predictors become. So this is, if R calculates, if you think about how R calculates in the backstage, this is the first thing they calculate, then they transform it into odds, and then they transform it into the probability. So for our illustrative example, we're going to have 2 subjects that are 35 and 45 of years of old, years of age, and the behavioral risk score, we set them to be the same, and the race is the same. And if this is going to be set up, the new data is going to be set up as a new data frame. This is a data frame with 2 rows, 2 subjects, and the 3 variables. You need to have, this new data frame can have more variables than what you use in your model, but it has to contain all of the variables you use. So your variables in the model needs to be a subset of the variables in your new data frame. And then you just put the new data frame as new data. If you don't specify this, it's going to predict based on your training data. And if you specify the new data as the data frame, then doing the predict function will only give you the log odds, not the odds or the probability. So this is going to be something within negative infinity and infinity. This log odds is just a linear combination of predictors when you plug in. If you want to get the probability, you set type equal to response. It will make you the probabilities. Or you can manually obtain these, but it's not really convenient. So remember to use type equal to response to obtain the prediction. This is prediction of the first entry, the second entry, and they're different because the first patient is younger for this data set. And prediction, when we did prediction for linear regression, we had confidence intervals and prediction intervals, and we talk about the difference between those two. For logistic regression, prediction intervals are not quite useful because if you think about, we're predicting a probability between 0 and 1. So that interval is always going to be between 0 and 1. And in reality, when you look at the prediction intervals, the interval is always pretty large, a wide interval between 0 and 1. It doesn't really tell you much. So for logistic regression, we rarely look at prediction intervals, and we just look at the point prediction, the predicted probability itself. And the probability can then be used to classify patients. So sometimes you want to transform that probability into an action of intervene or not. Then you need a cutoff value. Logistic regression doesn't decide the cutoff value for you. You need to decide yourself based on different criteria. So very commonly seen cutoff is 0.5. If your probability of yes is larger than 0.5, then you say it's predicted as a yes, and otherwise it's predicted as no. But logistic regression when you run logistic regression, there can be situations where you have very unbalanced 0 and 1s. In those situations, you may want to adjust your cutoff values based on the prevalence of yes and no's in your training data and testing data. We'll go over that later on. But here, I'm going to illustrate how you can use logistic regression and the predicted probability to perform classification or grouping or prediction of labels instead of just a continuous probability. So here, if you look at the example where we have age and IgG as, so this is just for illustration purposes, we're using 2 continuous predictors now because this is easier to plot and it's more intuitive. The same logic will apply to categorical predictors. It's just hard to illustrate. So we're using 2 continuous predictors to predict the binary outcome of HIV status. If you look at this linear equation here, this is actually going to be a linear plane in the high-dimensional space formed by age, intercept, and IgG level. So suppose that we have a predicted probability of a subject after we plug in their age and IgG level, and we have that probability smaller than a pre-specified cutoff. You're basically describing the space on one side of that plane. So here is what I mean. So each dot here is one subject, X for age, Y for IgG level, and the color denotes the outcome of that subject. And here, each line is one regression equation. Is the regression equation for one cutoff. The purple line here is the cutoff 0.5. So on one side is the predicted probability larger than 0.5. On the other side is the predicted probability smaller than 0.5. And the orange line is the cutoff of 0.2. So on the right-hand side is the cutoff probability, is all the subjects with probability predicted as larger than 0.2. On this side, all of the subjects have predicted probabilities smaller than 0.2. And the green one here is the average of Y. These are different cutoffs you can use to transform that predicted probability into two groups. For our data set, because there are many more subjects that are actually not infected at 28 weeks. So there's a huge imbalance between 0 and 1s. In that situation, if you use purple, if you use the cutoff 0.5, then everyone is going to be predicted as on this side would be not infected. I think I was talking in the wrong direction. So on the right top corner, this side, on the right upper side of the line is not infected. On the lower side of the line is infected. But if you use the cutoff probability of 0.5, then everyone is predicted as not infected, and that is not going to be very helpful. So for this specific data set, it will be more meaningful to use the cutoff of the average of everyone. So this is basically the proportion. You use the proportion of having the proportion of ones as your cutoff. When you run a logistic regression with very imbalanced 0 and 1s, you should consider the cutoff as the average instead of the cutoff of 0.5. If you really want to choose a cutoff that is intuitive. Of course, you can choose other cutoffs based on some other criteria we'll discuss later, but these are the most common ones. The mean of the proportion of ones in your training data or the 0.5. And whatever cutoff you use, you're going to misclassify some of the subjects. For example, if you use the green line, the proportion of yeses, if you use this as the cutoff, then anything that is red on the upper side and anything blue on the lower side, those are your misclassifications. So very rarely you would have a clear separation of the yes and no's. In that situation, your logistic regression is actually going to return something quite bizarre. It's going to have non-convergence and very, very large estimated coefficients for some of the predictors. because your data is telling the model that there's a perfect separation of the points, and you can just keep increasing the coefficient without changing the accuracy of the prediction. So most of the times you will see something like this, the points mixed up together, and whatever regression model, whatever cutoff you use, you will have some points misclassified. If you have a perfect separation of the groups, then your regression output will tell you somewhere here, you will have extremely large estimated coefficients. Even if all your predictors are scaled correctly, you will have extremely large coefficients. That is actually telling you the model is not converging well, and there's a perfect separation of the points. In that situation, it can be a good thing or a bad thing. It means that your data are well separated and you don't need a very complicated model to describe the separation to describe the association between yes and no. You might have a very straightforward, accurate predictor for your outcome, yes or no, or you may just be overfitting your data. You have too many predictors and too few samples. So seeing a perfect separation of points in logistic regression can be a good thing or a bad thing. It can mean that your predictors are just strong, you have a perfect predictor, or you are overfitting and you have too many predictors and too few sample size. Here we talk about how the fitted regression model is actually imposing a linear plan in the high-dimensional space spanned by your predictors. And that plan can be parallelly moved to many different places depending on what cutoff you use to put the plan. So the cutoff determine where your plan is, and the regression coefficients determine the slope, how tilted your plan is. And depending on your cutoff, your observed data points, your new data points and your training data, your testing data, whatever data you have, will end up on different sides of the plan. And if you choose the cutoff of the mean average here, then this is the cutoff too. Then you will have a different table. You will have a table of correct and incorrect classifications. So on the x-axis, these should be the observed yes or no's, and on the y are the this is the setup of the table function I use here. This is the x variable that's observing 1 or 0, true or false. And on the y, on the columns, these are whether your predicted probability is larger than the cutoff or not. So if we choose the cutoff that's the green one, then these are the correctly predicted training samples, and these are the wrongly classified training samples. And if you take the proportion of the wrong ones over all the sample size, it will be the misclassification rate. So for this one, it's going to be about 37%. If you use the orange one as the cutoff value, then you will have a different table for the misclassifications. Again, the way I set it up is on the rows are the observed values, on the columns are the predicted values, and the off diagonals are the wrong ones. The diagonal numbers are the correct ones. And for this one, the misclassification rate is going to be 30%. slightly lower than what we use for the green line. So intuitively, if you don't have any prior knowledge and just choose a cutoff, you can choose the average or 0.5. But many of the situations that may not be the best cutoff in terms of misclassification rate. The predicted probability for a new subject that is 35 years old with this level of IgG, the person getting an HIV by 28 weeks can be predicted using this predictive function on the new data set. And if you want the predicted probability, you set it as type of equal to response. And you can then look at this probability, this new data probability, and decide whether it's below or above the cutoff. So for this specific situation, if I choose the green as the cutoff value, then this data point is going to be on the lower side of the it's going to be up. I think it's upper side is no, right? So it's going to be on the upper side of this plane. This new point is going to be 35 and 5. Oh, it's on the lower side. So it's somewhere here. 35 and 5. So this subject is here. The probability is smaller than the cutoff. So I guess the lower side is no, the upper side is yes. Hmm. There are the regression coefficients. Let's see. For this specific one, well, I don't have regression coefficients printed out. It's without the regression coefficients, it's hard to tell which side of the regression plan is. But this is just an illustration of how you use logistic regression to separate the whole sample space into two parts, with one part being yes, the other part being no, and you are going to have a different separation when you have a different cutoff. So that's the key take-home point. If it's on one side or the other, that is most of the times not relevant when you look at your output, because you never really plot this plot for your data set. This is just one example it's a visualization of that this specific data set to show you the concept of that separation of space. So when you fit a linear regression, you basically get a separation of the space into two parts. And that separation is dependent on how you choose the cutoff. And when you have a different cutoff, you have a different separation, you will have a different misclassification. Here is the one-dimensional look at this classification problem. So suppose we only use one predictor that's continuous. The IgG level, Y is your outcome variable. Remember, we said that it doesn't really make sense to fit a linear line to predict the binary outcome by continuous predictor. So this logistic regression is actually not fitting a linear line. It's fitting a logic function here, an x-weight function here, to describe the probability of each points, the probability for each of the IgG values. So for example, here at 4, when your IgG level is 4, then predicted probability of HIV equal to yes is this value, you are more likely to observe zeros at this point compared to one. And when you have, I mean, ones compared to zeros, so there are more ones here if you compare it to the zeros here. And on the right-hand side, when you look at IgG level equal to 8, then there are many, many more zeros compared to the ones. So your predicted probability of having yes is going to be lower on this side. It's going to be higher on this side. And if you choose the cutoff of this cutoff, then all of the subjects on the left-hand side will be classified as yes, and all of the subjects on the right-hand side will be classified as no, and you will have misclassification happening on the left here and on the top right here. Those are the misclassified points. Any questions? So like I said earlier, when you have a perfect separation of the points, it can be a blast or a curse. Here is one example when we have a perfect separation of the points. So this is just a simulated data where I make sure the points are perfectly separated in the sense that all of the x that is positive are predicted have observed the y equal to 1. So all of the x positive values have y equal to 1, and on the other side have y equal to 0. There's going to be a perfect separation between the labels. You can basically use x to perfectly predict y. If you run a logistic regression with this data set, y against x, you will see your regression coefficient being super large, and your residual deviance is super, super small. So this is telling you, even if your x is well scaled, the regression coefficient is this large, there's an inconvergence of the model because you have perfect separation. Your coefficient can change, can just change regardless of the model prediction accuracy. This value can change to even larger numbers without changing the model fitting, because your model fitting is almost perfect. And here is a 2D example of a perfect prediction of y. So here I have two predictors, x1 and x2, and the two variables in combination will perfectly predict y. Using one of them doesn't perfectly predict y, but using a combination of them will give you a perfect separation of y. This is more commonly seen, especially when you have high dimensional predictors. When you have a data set with a lot of predictors that are intertwined with each other. Some are correlated with each other. Some and sometimes you may have more predictors than the number of samples. In that situation, you might be able to find some combination of the predictors to have a perfect prediction of the outcome. So it will create a separating plane here that give you no misclassification of the training sample. If you run an example like this, again, you will see the residual deviance being super small. That's saying that the model is almost perfect, and the regression coefficients are going to be super large in terms of scale, regardless of the size. So when you see something like this, you wouldn't trust your estimation out of the model directly. You would want to investigate whether your number of predictors are too big. Is it doing a perfect overfitting of the data set? Or is it because of a few predictors actually doing a really great job? So you would want to investigate into that by looking at some visualization, for example, plotting each of the individual predictors against the outcome, double checking if there is a lot of collinearity in the predictors we'll talk about later. So there need to be some investigation into the data set to know why this is happening. For logistic regression diagnostics, this is much simpler than linear regression because the model setting for linear regression has the normality, the homogeneity, and the linearity in the model setting. But for logistic regression, there's no normality, there's no heterogeneity. You're basically checking if your predictors are if your samples have outliers or not. So here we are going to use the Cook's distance or the leverages to check for the outliers. I think this is something that I skipped from the last lecture because I wanted to talk about when I talk about the diagnostics, I only talk about the normality, heterogeneity, and linearity. I forgot to talk about the outliers in after the break. But the idea is to diagnose for outliers between linear regression and logistic regression are very similar. So the leverage is one quantity, the Cook's distance is the other quantity. If you look at the leverage, this is saying whether your X is an outlier. It doesn't necessarily mean that your outliers are affecting the model fitting very much. It's just saying that this specific sample, it's on the top. It has an X that is very different from the rest. So it may be an extremely old individual in the population of an extremely young cancer patients among a bunch of old cancer patients. So that age can be an outlier in terms of predictors. That is quantified by leverage. And the Cook's distance quantifies the overall influence of the data, the overall influence of any given training sample on the whole model fitting. So the number of lines is the total number of training samples. And the lines that are longer are the ones are the training subjects that have the biggest impact on the model fitting. So most of the times you will see them being relatively comparable to each other, but in some of the situations you may see the Cook's distance jumping out compared to the rest. If you have a pretty large sample size, then you may want to you may have some luxury to remove some of the outliers, then these are the samples you should consider removing if you see the Cook's distance being very large. So those diagnostic plots are the ones you can use to detect for the outliers in X and the influential points. These are the influential samples on your model fitting. And to obtain the diagnostic plots, you can use the plot function on your model fitting, and by specifying which you're asking the for specific model diagnostic plots. And for this specific one, the Cook's distance and the leverage are the relevant ones for outlier diagnostics. And here, these three correspond to the 1, 2, 3, 3 plots here. For the last one, for the leverage, you can obtain it by using the hat values on the regression output to obtain the leverage points. So 1, 4, 5, and this is separate. And then you can check which one of them has the largest Cook's values, Cook's distance. So for example, this function Cook's dot distance on the outcome is going to get the Cook's distance for all of the training samples, and you can then identify which one of them are the large ones, and you can identify the subject ID or the row ID of that subject, and then investigate on the specific values, the predictors or the outcome values of these variables, and then see if they actually are problematic or they should be kept in the model. So here I'm giving you a very artificial outlier where I just make that patient very likely to, so there is one of them that I changed. I make the X value being very different from the rest of the population. So for this one, it is I specify it as a 25-year-old, and it has observed HIV status of 1, but I make the IgG level equal to 50, which I think is pretty low for this specific data set. I forgot the distribution, but this is going to be these two values are going to be very different from the majority of the data set. And if you use this based on the rest of the data set, if you have this age and IgG values, it's more likely you have HIV equal to 0 instead of 1. So it's going to be very different from the rest of the samples in terms of X, and it's also going to have a very abnormal predicted abnormal Y compared to the rest of the data set. So in terms of outliers, this is an outlier of both X and overall Y value. And after I change this data set, after I add this outlier subject into the data set and running the logistic regression again, you can see this artificial sample jump out in terms of both leverage and Cook's distance. So these are situations when you would want to look into the data set and see whether you have a error in the recording of the X or that is actually a meaningful sample you want to consider or not. Questions? So that's logistic regression. When we talk about the perfect fitting of the logistic regression, we look at the deviance in the output here. Here, the residual deviance. So this is actually an evaluation of how well the model is fitted. We have something like this for both logistic regression and linear regression. So for linear regression, you have adjusted R-square, the AIC, and the BIC. These are all criteria describing how well your model fitted your data. And for logistic regression, you have AIC and BIC that's dependent on the deviance. They also describe how well your model fit your data. But it's more than how well your model fitted your data. So suppose that you want a criteria to describe how well the model fits. You would also want to consider the complexity of the model. So if you have a very well-fitting model, but it's too complicated, it involves too many parameters, it may not be very interesting to you because of the lack of interpretability. It would be better if you can achieve similar prediction accuracy with much lower number of predictors. So a parsimonious model with good prediction, good model fitting, those are preferred characteristics of models. So here we're going to present these model criteria, evaluation criteria. They actually balance between both the how well the model fits the data and how complex the models are. The complexity of the model setting is described by the number of predictors in the model. So here, the P of a given model is number of predictors, and N is the sample size. So the adjusted R square is described as 1 minus the residual sum of squares over the total sum of squares, adjusted by these sample size and number of predictors. So if you look at the overall here, the RSS, the residual sum of squares, is going to be small if you have a this is saying if this is small, it means your model is fitting the data very well. But so if this is small, then your adjusted R square is going to be large. So adjusted square increase a more accurate model means a lower RSS and a higher adjusted R square. But on the other side, this is the number of predictors in the model. If this is large, then this is small, this is large, and this is small. So when your P is large, when your number of predictors is large, you actually have a smaller R square, adjusted R square. So this is accounting for a trade-off between the number of predictors and how accurate your model setting is, your model fitting is. In contrast, the R square, the percent of variance explained by the model, does not have the P here. So, and it doesn't have the n minus P and n minus 1. So it doesn't adjust for the complexity of the model setting. So the more predictors you put in the model, the higher the lower your RSS is going to be, the higher your R square is going to be. So you're always going to get a higher R square by adding more predictors in the model. If you use R square to choose a good model, you are always going to choose the largest model with as much predictor as possible to put in the model setting. But if you also want to account for you would also prefer a parsimonious model, you would want to use adjusted R square instead of R square. A bigger R square is not always good because it can mean you're just fitting with too many predictors. So that's our adjusted R square. The AIC and the BIC are two other criteria you can use to evaluate models, to choose models. They both account for the model fitting accuracy, RSS, and the parsimonious, the complexity model, the complexity of the model, the number of predictors here. You can use either one. Similarly for logistic regression, for model setting. I'm not going to go over stepwise regression here because of the lack of time, but in many of the stepwise regression, you can use one of them to choose whether you want to reduce the model or increase the model by one predictor. These criteria will help you choose between different models in stepwise regression and finalize your to obtain a final set of predictors that do a reasonable prediction of the data set without using too many predictors. So to obtain AIC and BIC, you can just apply this function on the linear regression output or logistic regression output. I just realized that when I talk about logistic regression fitting, I didn't go over the code for running. So here in logistic regression, everything is set up as the linear regression, the same way as linear regression, with this exception. So you use the GLM function, and you specify the family equal to binomial. If you do not specify a family equal to binomial, it will by default run linear regression instead. Questions?
A quick question about the model evaluation criteria.
Mhm.
So sometimes in reality, or when we're doing some like the real data set, for example, if we compare two models, one of them will give us like the smaller AIC and another one has a smaller BIC. So I just wonder, how would you balance between the AIC, BIC when you decide which model is better?
Oh, that's a great question. So I think the BIC put more weight on the parsimonious of the samples, as you can see. The weight in front of the number of predictors for BIC is log n, and the weight in front of AIC is 2. The rest of the things are the same. So BIC puts more emphasis on the parsimonious of the data set, if that's what you value.
Okay, so if we prefer more parsimonious model, we should rely on BIC instead of AIC.
Yeah.
Okay. Thank you.
Thanks for a question. So that's the model evaluation criteria for logistic regression and linear regression. And we also have so that basically wraps up the logistic regression part. So now we know how to do prediction classification for a binary variable. We can move on to more categories. Instead of 0 and 1, we can have multiple categories. And in that situation, we need to generalize the binomial distribution into something we call the multinomial distribution. So multinomial distribution will have will basically, instead of having 2 categories, you're pitching multiple categories, 1 pair at a time. So suppose we have k categories, you're going to, in logistic regression with 2 categories, you just have p probability of 1 over 0. But now you have more than 0 and 1, you're using you're going to contrast the probability of 1 categories over the baseline group. So the first group chosen as the baseline, and you're going to model the probability of each of the remainder categories over the first category. So red, yellow, blue, if red is the baseline, then this is modeling the probability of yellow over red and blue over red. And all 3 of them should sum up to 1. So this is generalizing, but in a similar way, where you take the probability of the ratio of 2 probabilities, and this ratio is going to be connected to the linear combination of the predictors. For yellow versus red, you have 1 set of regression coefficients. For blue versus red, you have another set of regression coefficients. And when you have yellow versus red and blue versus red, the yellow versus blue will automatically be inferred from the previous 2 ratios. So in the end, you can express the probability of each category using these linear regression coefficients and ratios. They look really complicated, but they are essentially the generalization of logistic regression model. Instead of having a very simple numerator, we now have the summation of a lot of linear combinations. So logistic regression is just a simplified case of multinomial logistic regression with only 2 categories. And this is a very convenient model setting, but it also has one assumption, that is the independence of irrelevant alternatives. So the probability between red and yellow is independent of the probability of the rest of the categories. So if you compare two categories, their ratio of probability has nothing to do with the other categories. That's the independence of irrelevance alternative assumption. That may not be true, but it's a reasonable assumption to have. So the model setting is just taking the probability of ratios and to run the to estimate the parameters to run the regression model. I'm going to use a data set that's different from, that's not in the medical care realm. So this is a data for wine, where you have the chemical and physical characteristics of the wine, and we're trying to predict what type of wine it is. So this is just for illustration purposes. For this wine data, suppose we're just using two predictors, the color of the wine and the alcohol content of the wine, to predict what type of the wine it is. Then this is how you run it. You use the multinom function in this library, in this R package. And when you summarize, you will actually have, you will end up with several tables of regression coefficients as one. For this specific data set, I have 3 wine types. So 1, 2, 3, those are the 3 wine types. The first one is going to be automatically chosen as the baseline level. So the first set of coefficients here, this first row is comparing the type 2 wine compared to type 1 wine. This is comparing type 3 versus type 1 wine. So the regression coefficient here is telling me if I compare type 2 versus type 1, then the alcohol content in type 2 is much lower. And the color of type 2 is also lower. And this is comparing type 3 versus type 1. The alcohol content is also lower in type 3. But the color is higher. So a higher color and a lower alcohol content means wine compared. And by plugging in these coefficients, you will be able to obtain a probability of having. So this is my data set. In the first 10 rows. So I'm trying to predict my whole data set's probability of being each type of wine. I will end up with an n by 3, 3 being the number of categories of my data set. So the first sample, the first wine is predicted to be more likely to be type 1 compared to the rest. This second entry is more likely to be type 1 also, but less likely compared to the first one. So your predicted probability will be a table with multiple rows, each row representing one category of the response variable. And the summation of each row should be 1 because all the probabilities being each type, those 3 should sum up to 1. Any questions? So remember when you take the prediction of the multivariate multinomial regression to put type equal to probability to obtain the probabilities. If you just use the predict variable without the response equal to probability, it's going to choose the label for the largest probability. So it's going to predict 1 for this, 1 for this, 3 for this, 1 for this, 1 for this, 1, 1, 1, 1, and then 1. So it's going to take the largest probability and use that label for the label prediction of the sample. For this specific data set, if you use prediction, if you use the predict function, it will give you a bunch of labels, one label for each sample. And if you tabulate the observed one label and the predicted one label, this is your this is the table telling you how accurate your predictions are. The diagonal ones are the correctly predicted labels. The off diagonals are the wrong ones. So the misclassification rate will be the off diagonals, the summation of the off diagonals over the total sample size. Suppose you have a new wine that is alcohol level 13 and color equal to 4, then you can again use predict function with the new data setting. So before, if you do not use the new data, it's prediction on the training data. If you want new testing data, this is how you put it there. You can specify type equal to probability. And this is the predicted probability of the wine type for your new sample. So apparently this wine is more likely to be a type 2 compared to the rest. And so if you do not specify type equal to probability, it will tell you it's a type 2 wine. So the regression coefficients are interpreted in a similar way. It's going to be the instead of the odds compared one versus another, we now have 3 categories. So the odds are going to be the ratio of 2 probabilities, 2 versus 1, 3 versus 1 for each of the prediction equation. So here, this is giving you the regression coefficients for 2 versus 1. This is giving you the regression coefficients for 3 versus 1. If you plug these into regression equation, you will end up with the log odds of each pair of comparison. So if you look at this regression coefficients, this is saying that if I compare, if I want to see whether the wine is type 2 versus type 1, then increasing the alcohol level by 1 unit will make it more likely to be a type, it will make it less likely to be a type 2, more likely to be a type 1. And that probability difference is quantified by the exponential of this value. So the probability is going to be, the probability of type 2 over type 1 is going to be multiplied by exponential of this value if you increase alcohol by 1 unit. If you increase the color by 1 unit here, then the probability of type 3 versus over type 1 is going to be increased by exponential of 0.84. So the interpretation of multinomial logistic regression is slightly trickier than logistic regression, but the philosophy is the same. I encourage you to really look at the model setting when you interpret the regression coefficients like this. When you write out the regression equation, and on the left-hand side, you either use the log odds or in the logistic regression model or in linear regression model for the y. That really help you understand what is the exact connection between your predictors and your outcome in terms of the regression coefficients. So the regression output only tells you 2 versus 1, 3 versus 1. If you want to get 2 versus 3, you will have to do some manual calculations, but it's not super difficult. You just need to subtract them, these two, to obtain a third pair. And then these coefficients can be interpreted. If you want to get the p-values, then I would suggest you to just recode the logistic regression, the multinomial logistic regression. So in the data set here, you can the response variable type is coded as a factor variable with 1 as the baseline, the first factor level. If you want to get 3 versus 2, then I suggest you to recode the factor variable with 2 as the first level, and then you will end up with 1 versus 2, 3 versus 2, and you will get the standard errors and also the regression coefficients. So these regression coefficients can help you compare each pair of groups, but for multinomial regression, most commonly usage of it is to do classifications. So this is one example. This is just a visualization of how the classification works. In reality, you're just going to use the predict function, look at the probabilities, look at the highest probability for that classification. So this is the intuition behind the multinomial logistic regression. When we have 3 categories, the 3 colors represented by 3 colors, 2 predictors for the 2 axes. The multinomial logistic regression is going to fit 3 hyperplanes in this space. It's going to partition these 3 lines together. It's going to jointly partition the space into 3 sections. The green section with the highest probability being the green label, the type 2. So the blue section has the probability of type 3 larger than the rest of the 2. This section has type 1 having the highest probability. So if you jointly use the 3 regression lines, it will separate the planes into 3 sections, with each section having the highest probability for each label. And then when you have new data set, new data point, you can pinpoint whether that new data fall into any of the sections, and then predict the label based on where it falls. Of course, when you run multinomial linear regressions, you don't have to visualize everything. You can just look at the predicted probabilities and labels here. This is just an intuitive way of understanding how it works. Even though it's categorical on the Y, it is still a linear model because it's modeling the predictors in a linear way to connect them with the response variable. It's doing a linear separation of the whole space. So that's why logistic regression, linear model, and multinomial regression, they're all linear models predicting the outcomes. If you want nonlinear models, then you would want to use random forest or some other predictive modelings we'll talk about next time. So the last thing I want to cover before we finish is the evaluation of prediction accuracy. This is just for the, I think I should probably move the model evaluation criteria after this, talking about this. So this is just describing how well your wife is fitted by your data set. So the MSE is just taking the difference between your fitted Y and your observed Y, sum of them, doing a square, sum them up, and doing an average. The root means square error is just the square root of it. You can use either one. This is just describing how your prediction and your observation is from each other. You don't have to use it for linear models. Any predictive modeling, random forest, boosting, deep neural network, this is a good criteria to start with for continuous outcomes. And then there's mean absolute error. This one doesn't take the square, it takes the absolute value and then add it up. This is so the errors are not squared. Here the errors are squared. The difference between these two is that for the second one, it emphasizes less on the outliers. If you have an outlier here, after squared, that error is going to be really big. So it has a much stronger emphasis on those outliers. The outliers contribute a lot more to the MSE compared to the mean absolute error. So if you want your model evaluation to put less emphasis on the outliers, if you don't mind the outliers that much, then this is a good criteria to go with. And then there's variance explained. This is something that you see a lot, the R square. Again, this is the more predictors you put in there, the larger it's going to be. So sometimes just going with a larger R square can be a little misleading because it can bias toward the more complicated models. And it only evaluate the training sample. It cannot be used for out of sample prediction. The first two, these can be used either in sample or out of sample. The latter one, R square, can only be used for in sample. And these are some other reasons why we do not really want to use R square for model accuracy evaluation. So if you have Y with the same values of errors, then if your Y is actually falling in a bigger range, if your Y has a larger spread, then you will actually have a bigger R square. So the R square is taking into account the spread of the data and the error together. That may not be that may be misleading because you may have a really R square just because the spread of your data is very large. And the third one is that the R square can just it can be affected by the sample size and the noise level very much. R square that is very high doesn't mean that it's a right model. So here is a correct model where I just simulate data from Y equal to X, but it has a very high noise level. So this is a correct model. Just because the noise level is high, my R square is going to be very low. So the R square here is quite low. This is simulated data where X and Y are dependent based on a quadratic relationship. So Y is dependent on X squared. The model is definitely not right if you fit it with a linear model, but the R square is going to be very large in this situation. So a larger R square doesn't mean your model is correct or not. So R square can be quite leading in terms of evaluating how well a model is. So you do not see R square being used for model accuracy evaluation very often. The first two are the most commonly used ones. These are for model accuracy evaluation for the continuous outcomes. For categorical outcomes, we've already seen the misclassification error. That's the wrong labels over the total. And we also have, when you have only two categories, there are more criteria. So the most commonly seen ones are the false positive, false negative, specificity, the sensitivity, precision versus recall. These come in pairs. These two are the pair, one pair, these are one pair, and these are one pair. They evaluate the misclassification on two sides. You can be very conservative and predict everyone to zero. You can be very aggressive and predict everyone is one. But when you do these extremes, you will make one of them being zero and the other of them being very large. These two in combination will quantify, will be a good trade-off that you want to use together to quantify the model accuracy. For more criteria, I really suggest looking at this Wikipedia page where it has a lot of model accuracy criteria listed together and how they are connected with each other. So in general, there's a trade-off between these false positives and false negatives. If you look at the definition of false positives, they are taking the numerator here. The false negative is the numerator being here. These are the off diagonals. So if you go very conservative on one side, one of them will be zero. If you go aggressive to the other side, the other one of them will be zero. So there's a trade-off between these two off diagonals. And similarly with sensitivity and specificity, there's a trade-off between the off diagonals as well, because the and
I think you froze there for a second.
Oh, my internet was bad.
Yeah.
Sorry. Where did I start being frozen?
I believe it was false positives.
False positives? Okay. So false positives and false negatives, those are the two off diagonals of this 2x2 table comparing the observed versus the predicted labels. In general, there's a trade-off between those two. If you try to predict everyone being one, then you have this being very large and this being zero. If you predict everyone to be zero, then this will be very large and this will be zero. So you don't want to go if you want to go somewhere between those two extremes, then you are basically trading off between these two false classifications. So there's a trade-off between those two, and specificity and sensitivity, those are directly related to false positive and false negative. It's just another name to use. So there's also a trade-off between those two. And precision and recall is another pair. Recall is the same as sensitivity, but precision is not the same as specificity. It's 1 minus FDR instead of false positive rate. The false discovery rate is a slightly more complicated object here, concept here. It's the proportion of true positives among all positive discoveries. So it's the denominator, instead of being all observed ones or all observed zeros, it's actually related to how you make your decisions. It's how much it's related to how many in total you're predicted as one. The rest of them have the row sums being denominators. Precision and FDR are the only ones having the column sum as the denominator. So that one is going to have both the numerator and denominator change when you change your classifier. All of the rest will have the denominator unchanged when you change the classification criteria. Related to these concepts are the area under the curve. So there's one curve for the sensitivity and specificity. That curve is called the ROC curve. So it plot the sensitivity against the specificity, or 1 minus specificity. And the area under that ROC curve will quantify overall how well the model fits. So here is one ROC curve as an example. I'm running a logistic regression. The logistic regression is going to give me a bunch of predictive probabilities for each sample. And I can use any cutoffs. For one cutoff, I may have false positive and false negative. For this cutoff, I have false positive rate at here and sensitivity at here. If I change my cutoff, I will end up with a different false positive and different false negative. Change my cutoff, I will get another set of those values. If I gather all of the cutoffs and gather all of the false negative values, false positive values, I will have a curve. So this curve here doesn't depend on the specific cutoff you use for logistic regression. It's going to evaluate all cutoffs and see overall how they fit. And if you have a model that fits very well, that predicts very well, then this curve will mostly be above the diagonal line here, which means that for some of the cutoffs, you will have a very low, when you can get a low false positive while keep a low false negative. This is 1 minus false negative sensitivity. So you can have a high specificity and a high sensitivity at the same time. That's a good model. If your ROC curve is near the diagonal line, it means that you have you cannot keep sensitivity and specificity both very high. They're both mediocre whatever cutoff you use. There are situations you may end up with a ROC curve that is below the diagonal line. That mostly happens when you plot the ROC curve of a testing data. It means that your model is trained to fit the training data so well that it's actually not generalizable to your testing data. You're overfitting. So your model is describing worse than random in your testing data. In those situations, your ROC curve will be below y equal to y, and your sensitivity and specificity are both very low at the same time. So remember one thing, ROC curve for logistic regression, it doesn't involve any cutoffs. It's an evaluation of logistic regression for all of the cutoffs together in terms of a curve. And the area under the curve is the larger the better. If it's around 0.5, then you're basically not different from flipping a coin. If you're above, then your model is doing better than a random. To obtain the ROC curve and the area under the curve, you can use the ROC function. There are many other packages, but this is the one I use for this illustration. So to obtain that ROC curve, you need to have the predicted probability and the observed probability. So here I'm getting the predicted probability into a vector. This is on my training data. I obtain the predicted probability of the training data in this vector, and then this is the observed label of the training data. I do the ROC on both vectors. It will give me a curve and an area under the curve. This is another function, another package that people use to obtain the ROC curve. For this one, you use the predicted probability of the cases in one input, the predicted probability of the controls, the zeros in the other input, and you specify, I want to plot a curve, I will also give you an ROC curve. And this ROC curve has color in there. The colors are the predicted probabilities. So on this side, the predicted probabilities, the cutoffs. So on this side, the cutoffs are around the 0.4. On this side, the cutoffs are around 0.1. So when you change the cutoff, you have a different sensitivity and specificity. And this is evaluating all of the cutoffs. That's the ROC curve evaluating false positive, false negative, and false negative for logistic regression. The ROC curve is very good when you have a relatively balanced 0 and 1s in your data set. It can be overly optimistic if you have a very imbalanced data set. For example, if you have 90% of the data being 0 and 10% of them being 1, then you're not going to do a super bad job by predicting everyone equal to 0 in general. And you will actually get a pretty large AOC, the ROC under the curve, area under the curve in that situation. In those situations, many of the machine learning community recommend using the precision recall curve. So that one is going to account for the imbalance in the data set much better. Because it will consider the proportion of the positives, the ones inside all of the samples. The area under the curve for a random useless classifier is going to be the proportion of positive cases, ones in the data set. It emphasizes more on the performance of the classifier on the positive cases instead of treating the two classes, one and 0, the same. For ROC curve, if you swap the 0s by 1s and 1s by 0s, you are going to have the same thing. Your conclusions is not the different. Your ROC curve treat 1s and 0s equally. But for precision recall, it's going to emphasize more on the 1s. It tries to be a good classifier for the 1s. So for example, if you have a data set where you really do not care about misclassification of 0s, then you would want to use the precision recall as the evaluation. For example, in one of my research projects, we have the preterm birth as the outcome. And preterm is among most of the pregnancies, preterm is a minority. So you want to make a better prediction, a better classification of the preterms instead of the other way. In that situation, I would code preterm as 1 and term birth as 0 when I use the precision recall for model evaluation. So for your ROC curve, you are going to see a non-decreasing curve like here. But for precision recall, it's not always monotone because there's not a monotone relationship between precision and recall, unfortunately. But still, you want the area under that curve to be the larger, the better. And you would benchmark it against the proportion of ones in your data set. If it's larger than that proportion, then you have a more than random a classifier that's better than flipping a coin. I think I'm already over the time. These are mostly geared towards more quantitative background people. If you're interested, you can read why So what happens if a precision recall curve? What happens to a precision recall curve if you do a very extreme labeling of all of the samples equal to net zeros or ones, and you will see why what the sensor classifier like this, what the precision recall curve would look like. Any questions? I think the take-home message for this part is first, do not use R-square for model evaluation. Use MSE or MAE when you compare different machine learning models or predictive modelings. The second message is that there's a trade-off between false positive and false negative, and to evaluate the overall performance of logistic regression or classification model, you would want to use ROC or precision recall. And precision recall is preferred if you have very, very imbalanced label 1 and zeros, or when you have much more emphasis on the misclassification for one category compared to the other. So that's all I want to talk about the evaluation accuracy. Any questions? In the past years, these materials are for 3 hours, but now we have 2 hours, so I'm rushing towards many other things. If you have any questions, feel free to shoot me an email, and Richard and I can both answer your questions.